This is the Planck satellite's map of the cosmic microwave background. By measuring the universe as it existed roughly 13 billion years ago, Planck established a baseline expansion rate, the Hubble constant, of 67.4 kilometers per second per megaparsec. Measurements of the local universe show a different result. By calibrating local distances using Cepheid variables and supernovae, the SHOES collaboration measures a local expansion rate of 73.0. For over a decade, researchers have scrutinized both methods for calibration errors. Across completely independent local techniques, from the tip of the red giant branch to surface brightness fluctuations, this 9% discrepancy persists. Mode identity theory suggests that both values are physically correct. They represent the expansion of the universe sampled from two distinct physical conditions. The Hubble tension is a structural feature of the universe. It requires a deterministic mechanical explanation rather than a search for observational error. This mechanical explanation begins with mode identity theory. It posits that cosmological observables are drawn from specific positions on a topological wave called the 120 domain lattice. The cosmic microwave background records the universe in its bare state. When this light was emitted, localized galactic structure had not yet formed. Modern local observations occur in a different environment. Our telescopes are embedded deep inside a developed, flat-curved disk galaxy. This galactic structure creates a phase field. For an observer inside a rotating disk, the local environment shifts the sampling position on the underlying lattice. The 9% discrepancy is the result of this environmental phase shift. We can derive its exact value by mapping the geometry of the lattice. Cosmological observables emerge from fixed coordinate points on the 120 domain lattice, known as Fibonacci wells. This plot shows the phase operator wave, 2 sine squared of pi theta, dictating how parameters scale. The geometry fixes the Hubble constant bare well at a specific coordinate, 34/120. Sampling this unshifted position produces the baseline 67.4. This provides the starting point for the tension. Any local deviation from 67.4 corresponds to a specific movement along the logarithmic slope of this curve. The physical force driving that specific movement along the curve is the rapid internal rotation of a flat curved disk galaxy. A galaxy's rotation defines its coherence boundary, roughly 13 kiloparsecs for the Milky Way. Integrating the potential drop from this boundary to the galactic center reduces to a simple trigger index t, 2 times the rotational velocity squared, divided by the speed of light squared. We compare this index against the critical threshold required to trigger a phase shift. The ratio between the trigger index and the threshold yields a universal closure identity of approximately 2.2. Since both terms scale with velocity, this ratio is the same for every flat curve galaxy. Because 2.2 is well above the required threshold, every flat curve disk galaxy universally triggers a phase shift for its internal observers. When the trigger fires, it shifts the observer's sampling position by a discrete quantized step. The size of this step is fixed by the lattice. Cosmographic measurements, like photon redshifts, access only the bosonic projection of the lattice, which sets the minimum step at exactly 2/120. Adding this offset moves the sampling position from 34/120 to 36/120. The wave output increases from 1.208 at the baseline to 1.309. The ratio between these points is 1.084, an exact 8.4% increase. Applying this 1.084 ratio to the 67.4 baseline outputs 73.0. The local measurement emerges directly from the geometry of the lattice. This mathematical shift determines how different astronomical methodologies record the expansion rate. The final value depends on where they set their absolute calibration anchors. Local distance ladders anchor their starting points to standard candles located inside the coherent phase domain of their host galaxies. This leads to calibration inheritance. Because the starting ruler is biased by the local phase field, every subsequent rung on the distance ladder inherits the full 8.4% increase. Geometric methods, such as standard sirens or time delay lenses, utilize phase domain averaging. These methods integrate the expansion rate over billions of parsecs. The shifted local domain accounts for a microscopic fraction of the total path. Because the signal spends most of its journey in the bare well, true geometric methods should return a value near 67, provided they do not incorporate local distance ladder priors. Observational measurements are therefore stratified by their anchors. Methods calibrated inside a galactic phase field yield 73, while those integrating outside of it yield 67. Mode identity theory is mathematically rigid. It cannot adjust parameters to fit new data, making its predictions highly falsifiable. Because the galactic trigger is a binary function, the resulting Hubble measurements must be quantized. This leads to the discrete versus continuous test. Expansion data must cluster at 67 or 73, creating a bimodal distribution. If observations show a smooth gradient filling the gap between them, the quantized phase shift is falsified. A secondary test involves galaxies in cosmic voids. If their halos are underdeveloped and fail to reach the trigger threshold, they should theoretically return values closer to the bare well of 67. The tension between Planck and SH0ES represents a significant observational achievement of the decade. This 9% discrepancy provides an empirical window into galactic phase field mechanics. It aligns the expansion of the universe with the discrete geometry of the 120 domain lattice.